KURINJI Senior Secondary School, CBSE, Numerical.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
With this class, we are going to start a new chapter to discuss numericals. Okay, right. The chapter name is Dual Nature of Radiation and Matter. Dual Nature of Radiation and Matter, right? It is the first class. So we start with example problems. Then we will go for exercise problems. Afterwards, we will go for additional exercise problems. Okay, right. So you please be concentrate. First example problem. Okay, right. See this. Monochromatic light of frequency 6.0 into 10 to the power of 14 Hz. Monochromatic light of frequency 6.0 into 10 to the power of 14 Hz is produced by a laser light. Okay, a laser. Full stop. The power emitted is 2.0 into 10 to the power of -3 watt. Okay, the power emitted is 2.0 into 10 to the power of -3 watt. Okay, right. So they have given frequency of light, that is what monochromatic light. You know, that is 6.0 into 10 to the power of 14 Hz produced by a laser. Okay, light, that is what frequency of light, that is monochromatic light. Okay. Then he also given power emitted, that is 2.0 into 10 to the power of -3. Right. Next, two things he is asking to find. One is, what is the energy of a photon in the light beam? Second one, that is B, how many photons per second on an average are emitted by the source? How many photons per second on an average are emitted by the source? Okay, right. So two things we have to find. One is energy of the photon in the light beam. Another one is how many number of photons, right? How many photons per second on an average are emitted by the source? Okay, right. First we will go for A, then we will go for B. See here. This is what, you know, regarding the A, we are going to find photon energy, that is what energy of a photon. See here, the formula is E is equal to h nu, that is equal to 6.63 into 10 to the power of -34 joule second into 6 into 10 to the power of 14 Hz. That is equal to, right? So two things are here to multiply, and if you multiply, you will get the photon energy, that is energy of a photon is equal to 3.98 into 10 to the power of -19 joules. Next, B. In case of B, we have to find number of photons per second. Number of photons per second on an average are emitted by the source. Okay, right. And you know, here n is the number of photons emitted by the source per second, comma, the power P transmitted, okay, n is the number of photons emitted by the source per second, comma, the power P transmitted in the beam equals to n times the energy per photon. Okay, it's very simple thing, ma. See, when we are writing one formula, you have to know the terms. Okay, right, simple. So it is what power, and n is the number of photons emitted by the source per second, and E is the energy. E is the energy. Okay, right. And you know the relation, that is what power P, right? Power P transmitted in the beam equals capital N times the energy per photon. Capital N times the energy per photon. That is what you can say P is equal to N into E. Then N is equal to P by E. So P is what? This is what P value 2.0 into 10 power minus 3. And E is this value just now we found, ma, 3.98 into 10 to the power of minus 19 joules. Okay. So what is the SI unit of power? And as usual, you know, joule is the SI unit of energy. And do this division mathematically, we will get it as 5.0 into 10 to the power of 15 photons per second. 5.0 into 10 to the power of 15 photons per second. Okay, right. Next problem, that is example 11.2. The work function of a cesium is 2.14 electron volt. Find, here also we have A and B, so find A, the threshold frequency for cesium, and B is the wavelength of incident light. B is the wavelength of incident light if the photocurrent is brought to zero by a stopping potential of 0.60 volt. By a stopping potential of 0.60 volt. Okay, right. See here, the work function of cesium is 2.14 electron volt. Full stop. Find A, the threshold frequency for cesium, and B, the wavelength of the incident light if the photocurrent is brought to zero by a stopping potential of 0.6, right? Okay, because of the representation 0.60, right, recording the value 0.6 volt. Okay, right. See here, you know, we are going to discuss solution, right? So first we will discuss A and then we will come for B, right? So what are the given values here, ma? So the work function of cesium, that is what, 2.14 electron volt, right? And in A he is asking to find threshold frequency for cesium. You know the formula for threshold frequency, that is what, nu naught is equal to phi naught by h. Already phi naught value given as 2.14 electron volt, and h value given 6.63 into 10 to the power of minus 34 joule second. Okay, and that value whatever they have given, 2.14 electron volt, you can write it as, in place of phi naught, you can write it as 2.14 into 1.6 into 10 to the power of minus 19 volt, because volt is the SI unit. Sorry. Here electron volt is the unit of energy, no, right? So that's why this electron volt we are converting into joules. So you just imagine, ma, because of less space I didn't write here. Just in place of phi naught we are writing 2.14 into 1.6 into 10 to the power of minus 19 joules. And in place of h we are writing 6.63 into 10 to the power of minus 34 joule second. And if we divide these two, you will get it as 5.16 into 10 to the power of 14 h. 5.16 into 10 to the power of 14 h. Okay. So this is what threshold frequency according to the question. That is for cesium, for this value of work function, that is 2.14 electron volt. Okay, right. And they have written some information. It's okay, it's not a problem, simple thing, because what he told, ma, for the cutoff threshold frequency, the energy h nu naught of the incident radiation must be equal to the work function. That is what phi naught. So that you can say that is what nu naught is equal to phi naught by h, right. So for the cutoff or threshold frequency, the energy h nu naught of the incident radiation must be equal to the work function phi naught. So that nu naught is equal to, it's a frequency amount, phi naught by h, right. Substituting the values, this value here in joules and this value constant value in joule second, then we will get it as 5.16 into 10 to the power of 14 H. Next B, see here, right, A completed now B. The wavelength of incident light, if the photocurrent is brought to 0 by a stopping potential of 0.60 volt. So what he is asking to find? The wavelength of the incident light. The wavelength of the incident light he is asking to find. Okay, right. See this next. Photocurrent reduces to 0 when maximum kinetic energy of the emitted photoelectrons equal to the potential energy. That is what E V naught by the retarding potential V naught is a fact. Is the situation, what happened and what is present regarding that maximum kinetic energy and potential energy and stopping potential also. Okay, right. I will repeat once again because this information is important for us. Based on that only we will try to take the step to solve the problem. Okay, right. Photocurrent reduces to 0 when maximum kinetic energy of the emitted photoelectrons equals the potential energy E V naught by the retarding potential V naught. By the retarding potential V naught. Right? Okay. And then this is what Einstein's photoelectric equation is. E V naught is equal to Hc by lambda minus phi naught. Hc by lambda minus phi naught. Okay. So this is what E V naught is equal to h nu minus phi naught theorem, right. So in place of nu we have to write c by lambda. You can write c by lambda, and then E V naught is equal to Hc by lambda minus phi naught, or lambda is equal to, so we are writing lambda as a subject. If you write lambda as a subject, it's very simple, mathematically. E V naught plus phi naught is equal to Hc by lambda, and lambda is equal to Hc by E V naught plus phi naught. Okay, right. And H value, C value theorem. H value is 6.63 into 10 to the power of minus 34, right. 6.6 into 10 to the power of 6.63 into 10 to the power of minus 34, right. Joule second into C value is 3 into 10 to the power of 8 meter per second. Okay, right. Divided by, this value E V naught they have given as 0.60 volt. This is what stopping potential, right. Plus phi naught is 2.14. Phi naught is 2.14 here we have, right. So do this mathematical process, and joule second is the SI unit and meter per second is the SI unit, but electron volt is not the SI unit. You know how to convert electron volt into joules. That is, 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules, right. You just take it as that is what, it is like here you can say that, right. It is 2.74 electron volt, and you just replace this 2.74 electron volt with 2.74 into 1.6 into 10 to the power of minus 19 joule. Then no problem, because this one is SI and this one is SI, and now this is in also SI, right. Then finally we will get it as 454 nanometers, right. So first we will get it as in meters, and then you can convert into nanometers. Then lambda value will become as 454 nanometers. 454 nanometers. This is the wavelength of incident light if the photocurrent is brought to 0 by a stopping potential of 0.60 volt. 0.60 volt. Okay, right. And here itself, okay, right, we calculated in A, we calculated that is what threshold frequency, and in B we calculated that is what wavelength of incident light here, and here threshold frequency for cesium. Okay, right. Now we are going to see the next problem, that is example 11.3. okay, see here, the wavelength of light in the visible region, is about 390 nanometers for violet color, about 550 nanometers for yellow green color. This is average wavelength. It is average wavelength for yellow green color, and about 760 nanometers for red color. Okay, right. Next, here he is asking to find two things. One is A, another one is B. Right. What is A? What are the energies of photons in electron volt at the violet end? Next, average wavelength, that is for yellow green color. And third one, red end of the visible spectrum. Okay, right. Then B, from which of the photosensitive materials with work functions listed in the table 11.1, right? So in our theory, when we were in a discussion about the theory regarding the work function, there is a list in our textbook. You can see that, right? So in that list they have given some materials, the metals, and given the value of work functions. Okay, right. And using the results of 1, 2 and 3, which we are going to work out regarding the A. Okay, right. That is what here, okay, see this. So 1, 2 and 3 of A. Can you build a photoelectric device that operates with visible light? Can you build a photoelectric device that operates with visible light? Okay, right. And from our theory, we know the relation between wavelength of incident light, right? Wavelength of incident light and work function. Okay, right. Wavelength of incident light means energy of the incident light, and then work function, right? So what is the relation? And when photoelectrons comes out from a metallic surface, right? And when photoelectrons will not come out from the metallic surface, right? So this and all we studied. So based on that, and based on the values of work function given from some materials from the table 11.1, he is asking, can you build a photoelectric device that operates with visible light? Okay, right. And regarding this problem, first we are going to see A. After finishing this A, we will come to discuss B, right. See, come back to this discussion, that is what we had already regarding the A. And before going to discuss the A, it is better to see the given information. The wavelength of light in the visible region is about 390 nanometer for violet color, about 550 nanometers for average wavelength of yellow green color, and about 760 nanometers for red color. Okay, right. Here A is, what are the energies of photons in electron volt? What are the energies of photons in electron volt at the 1, violet end, 2, average wavelength, yellow green color, and third, red end of the visible spectrum. Red end of the visible spectrum. Okay, right. Come to this point. See, first we will discuss about, I told you, right. Energy of the incident photon, that is what E is equal to h nu. That is equal to hc by lambda. So, okay, right, we want to find E value in terms of lambda, because lambda we don't know, no, that's why, right. But hc value we know, because it is right, it is hc, that is we are multiplying here, it will give you 1.989 into 10 to the power of minus 25, 10 to the power of minus 25 joule meter, right, that is what joule meter, and in the denominator that is what lambda. Okay, so it is same, E is equal to 1.989 into 10 to the power of minus 25 by lambda joule meter. This is what energy, this is what energy, right, energy of the incident, energy of the incident photon, energy of the incident photon. E is equal to h nu, that is equal to hc by lambda, right. So, E is equal to 1.989 into 10 to the power of minus 25 by lambda joule meter, right. This is the energy of the incident photon, right. Now, we are going to calculate for violet light, for a yellow green light, for red light. So, we are going to calculate the energy, okay, right. And for violet light, he mentioned that 390 nanometers is the wavelength, see here, right, and that value we have to write here. This is same, that is 1.989 into 10 to the power of minus 35, 10 to the power of minus 35, and divided by this value will give us 3.19 electron volt, right, 3.19 electron volt. Okay, this is the value in joule meter, and this is the value in meter, and meter will get cancelled, and this is the joule. And afterwards you can convert joule into electron volt. You know that 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joule, right. So, here he converted, we can also convert, no problem, right. So, anyhow, for violet light the energy is 3.19 electron volt. Similarly, you can calculate for yellow green light, and you can also calculate for red light. Okay, for yellow green light E2 is equal to, just naming, it is what E1 and it is what E2 and it is what E3. Okay, for yellow green light E2 is equal to this value 1.989 into 10 to the power of minus 35 divided by 550, right, and that is here 550 into 10 to the power of minus 9, 10 to the power of minus 9. Okay, see here, that is equal to 2.26 electron volt. Okay, 2.26 electron volt, right. This value is 10 to the power of minus 25. So, already here I have written clearly that value only we are writing here, here and here, right. So, don't confuse, and it is not other value, it is just 1.98 into 10 to the power of minus 25 by lambda. So, in place of lambda we are writing the wavelengths of these things, that is what violet light, yellow green light, and for red light also. Okay, right. And for yellow green light it is, if you write 550 into 10 to the power of minus 19, we will get it as 2.26 electron volt as incident photon energy. This is what incident photon energy for yellow green light. Next, for red light, that is what incident photon energy E3 is equal to, same, you just substitute 760 nanometers, 760 into 10 to the power of minus 9, that is equal to 1.64 electron volt, 1.64 electron volt. Okay, right. So, whatever he asked, from that A we found all the things, that is what energies of photons in electron volt at the violet end, average wavelength yellow green color, and radiant of the visible spectrum, radiant of the visible spectrum as 1.64 electron volt. Next B. From which of the photosensitive materials with work functions listed in table 11.1, right, and using the results of table, right, using the results of 1, 2 and 3 of A, can you build a photoelectric device that operates with visible light? Okay, right. See here. We have to just compare. Nothing is there. It is very simple because you just compare. I already told you what is the relation between energy of the incident light and then work function. Okay, that's I already told you, and that only we are going to check once to answer for B. How can we build, whether it is possible or not? If it is possible, in what color it is possible and what color it is not possible. That's all. Okay, right. See here. For a photoelectric device to operate, we require incident light energy E to be equal to or greater than phi naught of the material. You know very well, when energy of the incident radiation is greater than the work function, the electrons will emit with a certain amount of energy, right? That's we are calling it as kinetic energy. Okay, right. But when the incident light energy equal to the work function, just the electrons will come out. After coming out, the electrons cannot go anywhere because of having no speed, right? That is the situation happens based on the relation between energy of the incident light and work function. Okay, right. See here. See this, ma. Thus, the photoelectric device will operate with violet light. That is, they have given in the bracket that energy, right? So for violet light, the energy is 3.19 electron volt, right? So the photoelectric device will operate with violet light, comma, photosensitive material, sodium, potassium and cesium, right? Sodium, potassium and cesium. In the bracket they have given phi naught, that is what, 2.75 electron volt, 2.30 electron volt and 2.14 electron volt. When compared these values, the energy will be greater here. That is what 3.19 electron volt. 3.19 electron volt, right? That is, because of these values, it is possible here. In case of sodium, potassium and cesium, it is possible. Then, if you go for C, it will also operate with yellow green light because it is 2.26 electron volt. 2.26 electron volt, and this value is greater than, that is what, see here, 2.26 electron volt. It will also operate with yellow green light, and see here, this is for cesium, phi naught 2.14 electron volt, and you just compare these two. This should be greater than this, right? So it will also operate with yellow green light with this energy value for this cesium, that is work function value only. However, it will not operate for red light. It will not operate with red light, that is energy is 1.64 electron volt for any of these photosensitive materials, because for all these photosensitive material the work functions will be 2.75 and 2.30 and 2.14. So this for red light it is what, it is only 1.64 electron volt. When the energy of the incident radiation is less than the work function, it is not possible, right? So that's why you can say that it will not operate with red light for any of these photosensitive materials. Okay, right. So this is all about third problem, example 11.3. Okay, right. So in this class we discussed the three problems, 11.1, 11.2 and 11.3. Okay, so go through this video again and again. Please try to understand every problem clearly, right, which helps a lot when we are going to solve the next upcoming problems. Okay, right. In our next class we will start with example 11.4. Okay, thank you.